Good night from Bloomington. This is Business Econometrics, and I'm Kerem Chakrar. And we will be holding a live session, and I'll start in a moment. But it is another cold day in Bloomington. I hope you are doing fine wherever you are. But how are you doing? How is the week going so far? By the way, this week is the Kelly Connect week. So are you enjoying the Kelly Connect week? Are you here? Probably not. But yeah, it is freezing out there. Like, it's so cold. Like I am like walking in a refrigerator or something. Okay, so but everyone can hear me and can see the slides fine, right? Where it's freezing from a tomato problem. Yeah, I understand what you mean. Tornado, yeah. Has anyone been affected by a tornado? Like anything happened there? Like I saw some very sad news about the tornadoes. There are people who who died, right, because of the tornadoes. Yeah, be careful, guys, right? I know there's sometimes there's no way to whatever you do, right? Tornado is there. Yeah, I heard that. Like it's terrible. It's very sad and it's very bad. Yeah, just rest in peace, right? Tornado. Yeah. So it's one of the random variables we talked about last time, right? Hitting an earthquake in a city or California and the flood. So that tornado is a random variable as well. But you can not predict sometimes how dangerous it could be. Anyway, today I'm going to talk about some statistics. And in fact, here is the live sessions, how it works, right? So I'm recording, by the way, this time. Can you see any signs that I'm recording on your side? Yep. All right. If you see that I'm not recording, please warn me. All right. Last time I thought the recording would start automatically, but it did not. And I started the recording this time. And hopefully, I am not going to make the same mistake again. All right. So let's start with a quick review of what we talked last week, right? Last week, after a brief introduction to econometrics, right, I started talking about the random variables. And in fact, econometrics is about predicting random variables, right? And we said our goal is trying to model the unknown and predict what that unknown is. So we are writing, for example, we are writing the demand in terms of a functional form of the price, and our random variables are the coefficients we would like to predict, which is like alpha plus beta times price, right? So we are trying to predict the coefficients of these functional forms mainly, and these coefficients are random variables. So we will be working with random variables, and today we're going to go over the statistic properties of these random variables and how to understand whether we are guessing the random variable right or not, right? That's the whole idea. But a random variable is a variable that takes different values from trial to trial, right, with experiment. And not every time you come up with the same value, but you may want to really be sure, maybe not 100% sure, but 95% sure of you are right, within some estimate. And that's our goal. And I talked about the normal distribution. At this point, I am pretty sure that you all know what normal distribution is, right? Any doubts about the normal distribution? It's a bell-shaped symmetric distribution with a mean mu and sigma square variance. And it's the most common continuous distribution. And we're going to mention central limit theorem today. It's basically the one that we see in the nature a lot. That's why we are using the normal distribution. We said the expected value is defined as mu, and variance is defined as sigma square when we have a random variable x with a normal distribution. We define the standard deviation as square root of the variance. These are all definitions that we mentioned last time. And this week, we are going to go over the statistics of the random variables given the central limit theorem and how we approach the unknown. But do you have any quick questions before we start? Here is how Zoom sessions will work. Week 1, week 2, week 3, right? So today, week 2, I am going over the topics that you have already studied last week. The whole point of the Zoom session is just to keep you kind of warm with the topics you have been studying, and in case you have a question from the part you have studied, this is the right time to ask. If I did go over this week's material, probably many of you have not started working on this week's material, right? So the live session would be not that valuable. Then we are going over the last week's material. So that's how it's gonna be. Okay, so that's why we are covering statistics overview this week, and next week we will be doing the regression analysis. So no questions, no quick questions. All right, so here's the plan. Today's lecture, right? I'll start with a brief discussion of transforming the normal distribution again. We'll solve some examples, and we'll try to understand the table of Z, how to read it. And I'll try to show you a very quick way to read the Z distribution, which is the standard normal distribution. Quick problem set number 1 due next Tuesday. Same as next lecture. Is it next Tuesday? That's not my, probably I will push it forward. I don't want it to be the same day as our live session. So I'll check it again. If it is next Tuesday, I will move it to Wednesday. Okay? Because I do not want it to be as the same days as the live session. In case you have a question about the problem set during the live session, I may answer it, and then you will have still 1 day to discuss, right? But still, if you have not started next Tuesday, it's not a good sign, okay? You should have started, and then you should have an idea what you are doing and what you cannot do, kind of, and then ask me the questions. All right, Dan? Okay, but I'll check the deadline for problem set number 1. I thought I had the deadline not Tuesday but Wednesday. So we're going to start with transforming the normal distribution again, but then we'll try to understand the data. We will not start with the data work, but we will understand the data. Sample versus population. So what is the difference, and how the predictions are different from a sample than from a population. So we will check the standard normal versus the t distribution, and then we will take a look at the mean and how we approach the mean. And then during the last part of our lecture, I'm going to talk about the interval estimates, mainly the confidence intervals, and what they are really for. Okay, it's very mathematical, but I'll try to walk through the examples and show you how to build the confidence intervals and what they are for. And then we'll finish the lecture with the hypothesis testing. There are a lot of things to talk about statistics, and it's not easy to talk everything in an hour or so. So if I go fast time to time, just don't understand anything, and you don't understand anything, just let me know. All right, but this is kind of the material that kind of we are assuming that you already reviewed, right? That's the point. So let's start with transforming the normal. So when we have a normal distribution, we can use the normal distribution characteristics to transform it to the standard normal. The standard normal has a mean of 0 and the same kind of bell shape as the normal distribution. But the advantage of having the standard normal is now we don't have to carry like 1,000 different tables or read different tables, but we can transform any normal distribution using the characteristics into a standard normal. Why? Why? Because we want to have a kind of a starting point to understand if our random variable that we predict is within our prediction values or not. Are we right? Okay, we are making the prediction, but are we right in that prediction? How right or how wrong our prediction is, right? That's why we need to understand the probability distribution function of that random variable we are predicting. So how do we transform? Here is the way we transform. Let's say we are interested in the probability of the random variable x being less than a. X is our random variable with a standard normal with mu and sigma square properties. Like mu is the mean and sigma square is the variance. Then how to transform? we subtract both sides mu. So basically what we are doing is we are moving, right? Moving the normal distribution to zero mean. And then after we move, we adjust the kind of the shape. We adjust the, the shape of the bell curve depending on the standard deviation. And then like we stretch or we shrink depending on the shape of the normal. Then we end up with this shape, right? We end up with the standard normal random variable. So we have a minus mu divided by sigma now is standard normal. Okay, so this is the way quickly we transform a normal distribution to standard normal. Now here's my example. Suppose we have the random variable x distributed with the normal mean mu and variance sigma squared, and we want to know if x is less than 2. What's the probability of the x random variable being 2? Now if you do not have the probability distribution function or probability distribution table, probability table of this normal distribution, then you can transform it. How? You subtract the mu from 2, right? 2 minus mu, divide by sigma. But we know what mu and sigma is, so we know what this number is. Then we just check the probability of the random variable z being less than 2 minus mu divided by sigma. All right, now I'm going to solve one more example that's going to show us with some values. But before we do that, here is how we're going to use the standard normal table. This is the standard normal table. Have you tried to read this? Have you practiced on reading some probabilities last week when you are reading the book? So in my table, here is how we read this. We take a value, right? Let's say 1.15. What's the probability of the standard normal being less than 1.15? It's gonna be like we have 1.1 here, but 1.15. So I go to here. So probability of the random variable z, which is standard normal, being less than 1.15 is gonna be 0.5 plus 0.3770, because you see the shape here. This is 0.5 plus this region, and the table is telling us what this region is. Since it's symmetric from the left end to 0, the probability is 0.5. So the probability becomes 0.5 plus 3.770. So it's 0.8770. Okay, so let's have an example. Okay, let x be a random variable where x is distributed normally with the mean 4, which is the expected value, and the variance 9, which makes the standard deviation is 3. Now what you see here is the variance, which is the sigma square. We take the square root to find the standard deviation, which is 3. So if I'm interested in the probability of the random variable x being less than 3, I transform it into a standard normal. How? We subtract the mean, like we move the mean to 0, right? 3 minus 4. Then divide by not the variance, but the standard deviation. So we divide by 3. So what we are looking for is, in fact, probability of the standard normal being less than -1/3. So I'll go back to my table. How would you read this? I want now -1/3, but I don't have -1/3 on this table. How would you read that? Probability being less than -1/3. How would you read that? Any ideas from this table? In fact, this table is enough. Greater than 0.33. It's symmetric, right? Exactly. And probability of z being greater than 0.33 is exactly probability of z being less or greater than -0.33. So how you do it? It's 1 minus probability, like you're gonna do 1 minus probability of x being less than 0.33. So where's 0.333? Here, right? 1.293. So 0.5 plus 1.293 is 0.6293. And 1 minus 0.6293 is exactly this value, 0.3704. So you have the probability of z being less than negative 1/3. Does that make sense? Now the next one, probability x being greater than 7. You make the transformation again. Now probability z greater than or equal to 1. Let's go back to our table again. 1 is 0.3413, but it is probability being less, right? If I find the 1 minus of it, I'll get like the if I have the probability z is less than or greater than 1, it's symmetric. It's gonna tell us this tail, right? This tail. So it's the 1 minus of it. So we'll end up with 0.1587. Now I want you to think about the last one. What if we have an interval, right? We want the random variable to be between 2 and 10. We transform both sides, and we transform the random variable into standard normal random variable, and we need to see the area between the points where we have negative 2/3 and negative 2. And then we read the table and we can calculate the area. But what's the total area? The total area is always 1 because it's a probability distribution function. Let me show you even more, right? Another example. Now, I want you to think about this example. For 30 seconds, I'll just, be silent, right? Not speak. And I want you to think about this example now. Okay, for 30 seconds. Okay. Now let's read the question. X is distributed normally. X is our random variable, but mu 160, sigma squared 900. What I want you to try is try to transform this. All right? Do you have pen and paper in front of you? Why don't you try to transform this, right? And write the new interval. We want the probability, but we want now z, not x. But what is z? It's x minus mu, which is 160, divided by sigma, right? Not sigma square, not the variance, but standard deviation, which is 30. Okay, and mu is 160. Can you write me the standard normal interval? Because this is the area we want, right? We would like to know what the probability of your random variable to be between 100 and 180. Sorry about that. So basically, the whole area is 1, right? If I measure this red area, that's the probability. Okay? Can you transform? Any questions about the transforming the normal? Okay, no questions. So let's do this together. All right, here's what I'm gonna do. I'm gonna apply this to both 100 and 180. So if I apply this to 100, right, it's 100 minus mu. 100, but mu is 160. Divide by 30. Okay, this is the first part. The other tail, this is the left tail, this is the right tail. The other tail, 180 minus 160, then divide by 30. And now we have the standard deviation, like, standard normal, random variable. And we would like to know the probability of this, which is exactly the same probability. Okay, does that make sense? Is it clear how we are transforming to normal? Because this is something we're going to use. All right, perfect. Okay, perfect. So let me clean my, it's clear. So this is basically, the next slide is basically what I did, right? So we have 100 minus 160 divided by 30, which is -2. So I would like to know the interval between the -2 and 0.6667 when the distribution is standard normal, and using the table, we can calculate that probability, and that probability is 0.725. Okay, this is how we transform the normal. So from now on, you know what I mean when I mean that, like, we are transforming into the normal, which we will use this, right? Transforming to normal when we are building a confidence interval. Could I show that on the table? Let's do that. All right, that's a great, let's show that. So first, what do we look for? There are two things you can do. All right, Alicia, like, first, we can read the probability of this, the whole thing, right? This part, like if I write this is A and the red part is B. First, I can read A plus B. Then I read A, then I'm gonna subtract A from A plus B. Okay, would that make sense before we start reading it? Okay, so let's go back to the table. Okay, 0.6667. So I'm going back to my table. 0. Okay, we don't have that precise here, but we'll take first this, right? So let's write that down. So my A plus B is, it's the probability of 0.666. So right, let me read now, right? This is, so it's gonna be 0.5 plus 0.2454. Okay, this is my A plus B. Now B, which is the probability of Z being less than -2, but we don't have negatives here, which means B is 1 minus, right? 1 minus probability Z being greater than 2. But what is Z being less than 2? Like 2, let's go. It's 0.4772. So the whole thing is 0.772. So that means this is nothing but 1 minus 0.9772. And then when we subtract A plus B, we'll get the probability. Okay, but is it clear how I'm getting this? If this is 2, right? If I'm reading this part, 1 minus of this part, then I'll get this part. Okay, how do I get, like, right here? Okay, yeah. So 2, right? You see this? This is this area, right? So this is 0.4772. But this part is 0.5. So the whole is 0.9772. Okay? All right, then 1 minus of it is the area we want. Okay? Then we can calculate it. All right? Of course, practice on this, right? This is not my first time doing this. The first time, you may not really grasp it, but as you start reading and more, you'll do better. And in fact, in the first problem set, I will be asking some of the applications of this, especially with the confidence intervals, because this is where the confidence intervals come into play. Okay, does that answer your question, Alicia? Okay. Now that we know how to read the probabilities and transform the normal distribution into a standard normal, Next, let's try to understand what we are after, right? How to use this when we are understanding the data, especially the statistical inference, and what the difference is between the standard normal and the t-distribution. Okay, sample versus population. Basic definitions. A population is the set of all elements in which the investigator interested. It's like if you would like to know how the votes is going to turn out in the United States of America, then the population is all the voters in the United States of America. But sample is a subset of elements, a set of observations. So a statistician won't really ask everyone. It's not feasible, but a statistician can choose a sample that represents the United States of America population, and that sample is going to represent the population statistically. And if you know every other, the data of every other population, it's called a census. And quite often the time you do not have the census, but you will have the sample, assuming that it's coming from a randomly chosen environment representing the population. But it's the difference between the sample and the population. Population is the whole set, sample is the subset of one part of the population. And if it is randomly chosen with some properties, which we will discuss, then sample is going to represent the population itself. So you don't have to know everyone, but you have to know only one sample. That's enough. That's the power of statistics, in fact. So what are the parameters we are talking about? Now, if we know the population, then what we know is population's mean, which is mu, and the standard deviation and the variance. But here's the thing. The population is going to be represented by the sample, and the mean is going to be represented by x bar, which is we're going to call it as the average value, right? Expected value, x bar. And the standard deviation is going to be s, and the variance will be s squared. But what are those, right? So let's discuss what those are. These comes from the variance statistics. You remember how we define those? Like S is gonna be expected value of x squared from the population minus, I'm sorry, this is x squared minus expected value of x squared, right? So this is how we get the s squared from the sample. If we know the population, then that's exactly what we want. But if we do not know the population, then we're going to take the sample and approach the right values of the population. That's the whole idea of statistics, trying to predict the right values. Okay, given those, some statistical properties. If the sample mean, sampling from a random variable x, we have the expected value of x bar gonna be mu x, that's what we're gonna call, and the variance of x bar, where x bar is again mu, right? The mean or the mean of the sample. Then we have the variance sigma square x divided by n, and the standard deviation sigma x divided by square root of n. So given those, we're gonna treat sample to understand how the real value coming from the normal. And we use the central limit theorem. That's the huge, like the most important theorem in statistics. And let me state what the theorem is. It's very mathematical and it's not easy to prove. But what central limit theorem suggests, as the sample size becomes large, your subset becomes larger and larger, the sampling distribution of the sample mean tends toward the normal distribution, which means that if you start randomly picking some set of the same random variable, 1 time, 2 times, 3 times, 4 times, right, different sets, the mean of these sets will be distributed normally. And that's what we're going to use. That's what we will, I'm not going to say assume, but we will take as the theorem and we're gonna say that no matter what the distribution of the random variable is, the sample mean of that random variable will look normal as n gets big. That's why it's very important to have big data, right? If you have the big data, then if you work in terms of regressional analysis, if you have enough observations, then every time your parameters will be as close as to the real value, because you will know the exact distribution of these sample means. Okay, that's the whole idea of the regressional analysis, because of the central limit theorem. Okay, now here is the property of the sample mean. When sampling from a normal population with mean mu, now again, the key part is here, the population, right? From a normal population with mean mu and standard deviation sigma. Now, not the population, but the sample, right? The sample mean, not the population, but sample mean, has a normal sampling distribution with mu mean. So it's going to have the same mean, but a different variance, because you are using too many, or you are not using the whole population. If you use the whole population, then you are going to achieve the same variance. But since you are not using the whole population but a subset, you kind of add this divided by n thing to kind of get rid of the errors you are getting. But as sample size increases, what does this imply about the sample mean? Can you tell? Like, as n increases, n goes to infinite, what happens? As you have more and more and more, what happens to variance when n goes to infinite? Less and less, like lower and lower variance, right? If this is the variance, but if n goes to large, this goes to 0. But what does that mean? If variance is 0 and you have a random variable, what does that mean? Now let's think like beyond these numbers. Like, what is 0 variance? You have a random variable with 0 variance. I want you to think about that. Any ideas? Variance is this, right? You see the random variable. Exactly, like you see the random variable. Sometimes it's one thing, sometimes other, right? How various your observation is. But if your observation is not varying, what does it mean? It's always, right? It's always what I observe. Exactly, what I observe is mu, always, all the time. I check and I observe mu, I observe mu, I observe mu. So my real number must be my observation. So that's the whole point, right? If we get infinite observations, we're gonna touch, we are gonna see the real number, but we will not have the infinite observations. But the more observations we have, the more likely we will end up with the real number with less variance. The variance drops, okay, with the mean. Does that make sense, what I'm trying to explain here? Does that have a term like distribution? What do you mean, like with 0? Like, there is no distribution, in fact, right? This is not going to be a random variable anymore. If there is no variance and you see only one outcome, that's the true value. It's not a kind of a random value anymore. So there's no distribution at all. Like, you see only one point, and that point is true. Okay? But of course, this is like a utopian way to think about this. There is no way we are going to approach the infinite observations. But the whole point of this is telling you, as the number of observations is higher, higher and higher, like you have more and more, your predicted value of the sample mean will be very close to the population's mean. Okay? All right. Now, let's brainstorm. Let's do some kind of thinking, right? Let me give you kind of a question here. Imagine I gave you mu, which means population mean. Okay, you know the population mean, but you had to estimate sigma using S. What would you do? All right, you know the mean, but not sigma. Then what you're gonna do is you will have a sample size of n, which is gonna be normal, right? Then you're gonna transform, right? You're gonna transform into a standard normal. Like what? Like this. X bar, your random variable, minus mu divided by S over square root of n. And that's gonna be a standard normal distribution. But since we don't know sigma, the standard normal is gonna be represented by the number of observations with n minus 1 degrees of freedom. And then that's what we call as the t distribution. It looks like a standard normal, but since we don't know the exact variance, it has greater variance, but becomes identical as degrees of freedom becomes large. Like if you have many observations, t distribution will be exactly the standard normal distribution. But if your number of observations is not too many, not enough, you switch to standard normal but t distribution. Then you control for that less number of observations. Okay, how is this useful? Here is how. We're gonna try to give some estimates, right? Try to predict, and then see if our predictions is right or wrong, right? Which is the hypothesis testing. Now, I'll give you another example. Suppose we sampled 100 people randomly, okay, randomly from our population, and asked their credit card balance, okay? Like, you know, we have this Kelly direct program. I'm taking randomly 100 people and I'm asking their credit card balance. And we get X bar as 15,740. But can you tell me what that X bar is now? What is that X bar? So how can I find this X bar? If I'm asking 100 people, what's the mechanics of it? Can you tell me? Which is the average, all right? So how can you find that X bar? Exactly, the mean of the sample. So you have all these numbers from 100 people, right? So you add all these numbers, right? 100 of these numbers. Then exactly divide by 100, and that's the mean of the sample size, but not the population. And you can calculate the standard deviation, and I'm just giving you this. There's no way we can calculate those, right? I'm just giving you this unless we have the data. But in the problem set, you will have the data and you will have the opportunity to calculate those things. So 842. Now, what's your best guess for mu, which is the average of the population in US, not the sample, but in US? This would be point estimate. What would be your best guess? What do you think? What would be your best guess? Point estimate, right? Like, I'm asking you, like, if I collected all the data from the population, what would be your best guess of the average of the population? I'll tell you, right? Your best guess is, again, the sample mean, especially if sample is coming from 100 people. 100 people, yeah, it's the sample mean, right? If it's 100 people, it's enough. So central limit theorem suggests if you have enough, then X bar approaches the mu. So that would be my best guess. Okay, X bar would be my best guess. But if I had only 3 people, not possible, right? It wouldn't give me a very nice estimate. But if I have 100 people, would be. But is it gonna be 100% right? Can we be 100% right? It's a point estimate. What's the probability of being us right? What do you think? What's the point probability of a distribution? because X bar is a random variable, exactly 0, right? My probability of being right at that point is 0. And this is like, like a dilemma, right? I'm making a point estimate, but my probability of being right is 0. But how can I increase that probability being right? Then we build confidence intervals. That's the whole idea of building confidence intervals. Okay, I will be 95% sure that the population mean will be some within an interval. Okay, so let's see that. Let's see how we are building these confidence intervals. All right, now we're going to estimate not the point estimate, because probability of being right is 0, but the interval estimates. Interval estimate, or as we call confidence intervals, is a range or interval within which population parameter is likely to lie. So we are trying to predict the population's mu. And by association, a measure of the confidence that the interval contains the population parameter. Of course, if you want a more and more precise, that interval must be larger and larger. But as you have a smaller and smaller interval, that confidence drops. And in fact, if you get a 1, that confidence becomes 0%. You will be 0% confident that mu will be that point. Okay, so we are going to use the sample mean as a point estimate, so starting point. So this is our best point estimate, and we are going to build the interval of guesses that we are highly confident will capture the true parameter. Okay, here is the process. But is the definition clear before I start showing you the process, building these confidence intervals? Is what confidence interval clear? Okay, so let's build it. Again, our goal is observing the sample mean. We are trying to predict the population mean, right? So population mean is the true value. If I know that, if I know the population mean, then I'm right. Like I know that. I'm trying to predict that. So here's what we know. In order to be 95% sure, I want my standard normal distribution to be between negative 1.96 and 1.96. This is our starting point. Okay, so how to reach that point? My sample mean is not standard normal, but it's a normal distribution. So I transform my sample mean using the mu and sigma divided by square root of n. This is the normal distribution of the sample mean. And if I know what the mu is, I know sigma and square root of n, then I'll get the values telling me in what interval my true value lies in when I'm 95% sure of the time. Like this is my left starting point of my interval, and this is my right. And I'm gonna be 95% sure that my true value is gonna lie between these two values. Let's go back to credit card example. I asked a point estimate from you, right? And you said 15,740. But now, if we build a confidence interval to be 95% sure, we have the X bar here. This is the mean of the sample, the credit card debt. We have negative 1.96 here. You want to be 95% sure. And this is the standard deviation you have divided by square root of 100. And then what we have is this number, the interval. But what does that mean? Let me explain one more time what it means. If we are going to predict what the true mean is going to be, which is the population mean, we are 95% sure that it's going to be between 15,574 and 15,905, which means, let's say these guys are keep coming in, right? I'm predicting one by one. 95 of 100 guys will have the credit card debt within this interval. 95 of those guys out of 100 guys. That's what we mean, really. So if you walk in and want me to make a estimation, right, then that's what I can tell you statistically. But if you want really the point estimate is this, right? I would say this. So my question to you is, would the point estimate be always within the confidence interval? What do you think? Let me repeat my question. Would the point estimate be within the confidence interval all the time? Exactly right. That's how we are building our analysis. For that reason, the sample size mean is so important, because we are building our analysis on the uncertainty. But one thing we are certain is the mean value. That's what we are going to use, in fact, when we are using the regression models, when we are trying to predict the parameters. Okay, we are building on the mean, sample mean. All right. Is the confidence interval clear? Does this mean that 2.5% will be above? No, it doesn't mean that. Like, they can be all scattered. We cannot control that. But what we are saying is, right, like for 100 times or 100,000 times, when we see these numbers, 95,000 times, these numbers will be within this interval. But we cannot control like 2.5 there or 2.5 there. Okay, that's not what it means. Okay. Then that would be like, then we would have we can also calculate the interval where you have 90% confident and 97.5% confident. But then what happens? This interval with 90% confident, it will shrink, but with 97.5 interval, it's gonna be larger set, right? What if you want to be 100%? What are you gonna take for 100%? What do you think? What's gonna happen if you want to be 100% right? 0 to infinity? Exactly, right? If you have the interval from 0 to infinity, you are 100% right. But you see how it's not possible, right? It's not possible. Like, you cannot be 100% right in statistics, but you are trying to get as close as you can. Even 97.5 is not going to be really realistic. Okay, do I have one more example? No. Okay, so in reality, right, like in data, we do not know sigma, and we had to estimate it with S. But here's the thing. When you have standard deviation coming from the sample, but not the population, then you may want to use the t distribution instead of z distribution. But when you have a large number of observations, like we have here, 100 observations with 99 degrees of freedom, then it's gonna be very similar to the standard normal. And in fact, what we see is, generally, if the sample size is large, then, oops, sorry about that. Where's this going? Let's go back. Previous. And let me erase this part. If sample size is large, usually 30 plus, but the more you have, the better the estimate will be. It's okay to use the standard normal rather than the t distribution statistically. And in fact, most of the statistical packages are using the standard normal, not the t distribution, when you have more than 30 observations. But when the sample size is small, like the one I will be giving you in the problem set, all right, when it's small, then you're going to use the t distribution rather than the standard normal distribution. And you can still build a confidence interval, but the precision of the confidence interval will be less. Okay, so it's the trade-off. The more observation you have, the more precise you will be, but you may still analyze the confidence, or you may still come up with the confidence interval even if you don't have many observations. So it's like 30, right? 30 is our like cutting point. And if you have 30 or more, you can switch to standard normal. Okay. So here's the summary, right? So what we will have is, right, with a small sample, we're going to use the t-distribution, but with the large sample, we're going to use the standard normal distribution. But if sigma is unknown, we're going to use the sample size standard deviation. With the large sample, we can use the standard normal, but with the small sample, we're going to use t. Okay, because we don't know exactly what the population standard deviation is. And this is basically how you can build the confidence interval. Given the t-distribution, critical values, that's what we call the critical values, s square root of n, you can build the confidence interval between x bar, which is your sample mean, minus the whole thing, like the critical value times s over square root of n, and x bar plus the critical value s over square root of n. Okay, but why are we building the confidence intervals? Can you think of a reason? Why are we building a confidence interval? Before we start the next part, let me ask you that. Why are we building the confidence interval? Okay, let me tell you why. Let's say I want to predict the demand for cars given the price, right? So here's what I will have. It's like alpha plus beta times price. Okay. So let's say I'm trying to predict this model where the demand equals to alpha plus beta times price. That alpha and beta are our random variables. Okay. And we would like to predict what that random variables are. Now, if I build a confidence interval, like 95% confidence interval, and let's say within the confidence interval, 0 is within that, I may not be right about my regression model after all. So we are going to check if these alphas and betas are the real values or not that we are predicting. And in order to do that, we're going to build confidence intervals, and to check whether we are right or wrong, we're going to test it, and we call it as the hypothesis testing. A hypothesis testing is a statement or assertion about the true value of an unknown parameter, which is like the mu, or which is like alpha here, or beta here, right? The unknown parameter. You start with a null hypothesis, saying that, let's say mu is 10 or not, right? Which is the alternative. Then we would like to know how likely that is true or false. So in a way, we would like to know if that value is within the confidence interval or not. If it is within the confidence interval, we are fine. But if it is not within the confidence interval, we'll fail to reject. I'm sorry, we reject, right? So how can we understand if we want to fail to reject or reject our hypothesis? Okay, so here's the process. A decision to reject or fail to reject, by the way, I'm not saying that we are accepting, right? I'm saying that we are failing to reject. These are two different things. If we reject, we are almost certain within the limits, but if we fail to reject, it's not certain, right? So if we are correct when the null hypothesis is true and it's not rejected, or the null hypothesis is false and it's rejected. So these are what we call as the errors, type 1 error and type 2 error. Okay, so we want to kind of minimize our errors. Like, we would like to be as certain as we could. But how could be we are incorrect, right? How could we be incorrect? Here's how we can be incorrect. The null hypothesis is true, right? So you have that hypothesis is true, but you are rejecting it. Then you would be wrong and you would be incorrect. That's what we call as the type 1 error. The probability of this event, in statistics, is denoted by alpha. And it is called the level of significance of test. So we are going to build our test depending on type 1 error. We want to minimize that error. But in order to minimize that error, we are going to get larger and larger confidence intervals. Then the second case is we are incorrect when the null hypothesis is false and is not rejected, right? That's called type 2 error. That's beta. The probability of this event is denoted by beta, and 1 minus beta is called the power of the test. By the way, you cannot control both. You can control either type 1 error or type 2 error, but you cannot control both. And quite often the time, we are trying to control type 1. We do not want to reject the hypothesis if it is true, right? So we're going to minimize this. We're going to minimize alpha. But you cannot make alpha 0, because if you make this alpha 0, that means you are choosing 0 to infinite, right? Your confidence interval is the largest, okay? Is the connection clear between the confidence intervals and hypothesis testing? Because here's the thing. Oops. Here's the thing. The confidence intervals are going to tell us whether our hypothesis is right or wrong. So when I am checking if my real value is 10 or not, then what I'm looking for is whether that 10, that value, is within the confidence interval or not. This is the connection. Does that make sense? The connection between the confidence intervals and hypothesis testing? Okay, because it's important, right? It's how the whole test is gonna be making sense. Okay. All right, so there are two types of, there are in fact two types of tests, two-tailed and one-tailed. We have the left tail and we have the right tail, but the two-tailed test is whether you want to know exactly a value or not. One tail is you want the real value greater than your estimated value, or you want the real value less than the estimated value. And we're going to check the probability of the event, and if that probability is too high, we will act accordingly. If it is too low, then we're going to act accordingly. So how? Let's see some examples. Here is how. With the two-tail test, we're going to check the confidence interval, and we're going to check if this A is within the confidence interval or not. And these points, like the alpha significance, when we have the 5% significance, we would like to make sure that we are 95% sure and 5% incorrect. Then you find these critical values, which is like this confidence intervals. And if this is between, right, then we are not rejecting, we fail to reject. But if it is outside, right, if it is outside, then we're going to reject. Okay, so all we need to do is find the value corresponding to the standard normal, and if that value is between the critical values, we fail to reject. But if it is outside the value, we reject. And it's the same with the right tail and the left tail hypothesis testing as well. We want to check this critical value, which comes from the transformation. I'll show you in a moment. But if it is outside the interval, outside this, then we reject. But if it is inside, we fail to reject. And it's the same with the right side. If it is right side of the value, then we reject. But if it is inside, like the left side, we fail to reject. So how to use this? Like, let's have an example. All right. So before the example, let me tell you how we're going to perform the test. We need a test statistics. So we will have the sample data, right? And we're going to compute the test statistics from the sample data. And its distribution is known, normally distributed, right? If the null hypothesis is true, we're gonna choose a significance level. Usually it's the 5% significance level, which means we are building a 95% confidence interval. Then we will find the rejection and fail to reject regions. We calculate the probability, and then we compare to the significance level of the test, and we conclude. So here is what we're gonna do. Example number 1. From a sample size of 40, let's say we have the sample mean as 20 and standard deviation of the sample is 4. Now we have 40. You can use the test statistics as the following. So I'm transforming the random variable here, right? X bar minus mu, which comes from the hypothesis, all right, divided by the S coming from the sample, divided by square root of n. So this is my test statistics now, because I know what the sample mean is, 20, minus whatever I'm testing, the real value in, then divided by 4 over square root of 40. Now, example number 2. Let's make the sample size. Let's make the test statistics. We have now 75 observations, but now we have sigma, right? Not S. Why sigma? Because it's 75 more. So we have, again, now standard normal, because we know sigma, not S. Then X bar minus mu H, so this comes from the test, again, 12 minus square root of 75. So we have the test statistics now. So we are going to use test statistics to understand the regions, fail to reject and reject regions. So what are we going to do? But any questions about the test statistics, how we are forming it? But you see the resemblance, right? What I'm doing is I'm transforming this to the distribution, the standard normal or t distribution, right? Given the normal distribution of the sample mean. Because we know that sample mean is normally distributed. That's the power of the central limit theorem. I know that this X bar is always normally distributed, okay? And using that fact, I am transforming it to the standard normal or the t statistics. Okay. So for what values of the test statistics will we reject? We need to understand the critical values. And for alpha 0.05, your critical values is negative 1.96 to 1.96. So if it is between these numbers, right, we fail to reject. Exactly. This is exactly what it is. Let me show you. Look, this is exactly what it is. Like, you see 97, like 0.0. The probability of Z being less than negative 1.96 is 0.025. This is how we are building the critical values. Okay, got it? Perfect. Oh, what? Let me erase everything, right? Just clear all drawings. Okay, we're gonna reject if Z stat is one of the tails. So let's find whether we would like to reject or not. Again, example number 1, right? If our test is, we would like to know if our real mean is 19 or not. Then all I need to calculate is the critical value. For the t distribution with 39 degrees of freedom, these are the critical values. And my test statistic is 1.58. Okay, this is my confidence interval, all right? And 1.58 is between these two numbers. That means I'm between the tails, so I fail to reject. So 19, in fact, this means what? 19 is within the 95% confidence interval. If you check what the confidence intervals are with 95%, you're going to end up with the numbers probably 18 point something to 20.2, and 19 will be inside. So we fail to reject. Is the example clear? Any questions about the example, the test statistics? Again, it all starts with the central limit theorem. Central limit theorem suggests the sample mean is normally distributed. And we use that, we transform it to t-distribution or standard normal. Then we check the critical values where the end tails have 0.025 probability. And then if the value we are checking is inside that critical values, then we are done, right? But if it is outside, then we reject. Okay, another example. If we have now a left tail example, then you see the left tail one, we basically on the left side negative infinity, but on the right side we have the critical value. So 1.58 is within the interval, then we fail to reject. What if I had 30 here? What do you think what's going to happen? What if I had 30? Would you reject? Let's go back to the test statistics. Like this, right? Test statistics is this. What if I, instead of 19, I have 30 here? What would you do? Would you reject? Fail to reject. Here is the thing. You're gonna fail to, you're gonna reject here, right? You're gonna reject because the value would be less than negative 0.23, the test statistics. So you're gonna fail to reject here. I'm sorry, you're gonna reject here, but you're gonna fail to reject. Because if mu is less or greater than 19, it's for sure it's less or greater than 30. So we fail to reject that as well. Because it's all about the sets, right? The possibility sets. Okay. We are almost there, right? So this is the way we test. We check the critical values depending on the one-tail or two-tail test. Then if the test statistics is within these values, we conclude, we fail to reject. But if it is outside, we conclude that we reject. There is another way to test. It's called p-value. P-value is the probability associated with the test statistics. Basically, p-value is telling us what the probability on the tail is. And if it is less, that means this. Let me show you on the graph. If p-value is less, then here is what we mean. Like if p-value is less than your values here, and the remaining area is less than your significance level. But if this is the area, then your value is within the rejection area. So when p-value is too small, then you reject. When p-value is large enough, then you fail to reject. Okay, does it make sense? Because you know the statistical programs, all the softwares will give you the p-value, and that's where the p-value is coming from the tail and the hypothesis testing. So we're gonna check p-value for the two-tailed and one-tailed tests. The p-value is the probability of seeing a more extreme value for the test statistics as compared to what was observed. But for a one-tailed test, the p-value is the probability of seeing a greater or smaller value for the test statistics. But here's the thing, again, p-value is the probability of the tail, okay, of the tail. Now, if we have two-tail, it's the probability of the sum of the two tails. So we have to be careful with that, okay, because it's a two-tail test. Let's go back to our example number 1 again. The test statistics was 1.58. For the two-tail test with alpha 0.05, p-value is 0.122. What does it mean? It means that, right, the whole value is way on the right side, so the whole probability is greater than the critical, like the rejection value. So we fail to reject because p-value is greater than alpha. So that's what we check. In short, we check if p-value is greater than alpha or not. If it is greater than alpha, we fail to reject the null hypothesis. But if it is less than alpha, then we reject. Now, a right tail test, we can calculate the p-value, which is 0.061. So p-value is still greater than alpha. What is alpha? Alpha is 0.025, right? So 0.061 is greater than 0.025. So we fail to reject. But which way you do? Like, you can go with the confidence interval, right? Or you can go with the test statistics and find whether the test statistics is within the critical values or not, or the p-value. The conclusion must be the same. You're going to either fail to reject or reject, depending on what your value is within the confidence interval or not. Test statistics is a way to understand if the value is within the confidence interval or not. Final note. In fact, p-value is telling us how big alpha must be to get a rejection. So it's the critical value of alpha. If the p-value for a given test is 0.122, that means for alpha less than 0.122, we fail to reject. But if alpha is greater than 0.122, we reject. So in a way, you can use the p-value to understand your type 1 error, how big or how small the type 1 error should be. So it gives us an idea how close we are to the null hypothesis, the p-value. And this week, right, we went over the statistics, but again, this is not something really can be understood totally in an hour or so, right? So make sure you read the statistics overview, because all the things we are building, these estimates of alphas, betas, the regression models and everything, at the end of the day, it relies on hypothesis testing, and it relies on the random variables of these alphas and betas and their properties. And we would like to understand if our estimates are right or wrong, or if they exist or not, right? And we're going to check that with the statistical properties that we have been talking. So we talked about the transforming to normal. We solved some examples. And then we said if we have a sample, the sample mean will have the normal distribution, which is the central limit theorem. And using that, we can transform that to get the standard normal or the t-distribution. And we can use the transformation to get a test statistics. And then we can see if the value we are interested in within the critical values or not. Then we reject or fail to reject our hypothesis testing. And we're going to apply this into the parameters we are going to estimate starting from next week. And next week, which is like this week, right? Next week, we are studying the regression analysis. We'll start with the simple regression models, and then the following weeks, multiple regression models. But from now on, right, we will be discussing the regression models where the parameters we are trying to predict is going to be the random variables we will be working with. The others will be the data. And hopefully you enjoyed today's statistics sessions, but make sure you review. If you have any questions, feel free to email me, but please read, all right? Please take the tests and make sure you start working on the problem set. I'll check the deadline and I'll adjust the deadline as well. So any questions before we conclude the night? It was so dense, I know, but is that a team assignment? Yes, problem set is a team assignment, but do not just assign the questions to one person. Make sure you work as a group, all right? I want all of the team members working on the problem set. Not to like problem set number 1, you do it. Problem set number 2, you do it, right? Just, you know, make a more collaborative work. Okay, any other questions? All right. Thanks for being with me tonight. And this is the end of this week's live session. And I will see you next week. Take care, stay safe, and stay warm. And have a good night, everyone. Bye-bye.